Hi, this is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and welcome to Module 6 of ME 566, Dynamic Modeling and Control of Engineering Systems. In Module 6, we're going to explore the notion of the computer simulation. And in this first mini lecture, we'll talk about the what's and whys of computer simulation. In other words, what exactly is a computer simulation and why do we do it? So let's get started. So in Module 6, we're going to cover, as I said, answer these two major questions. What exactly is a simulation and why do we do it? And I'll just jump to that. We simulate things because it's often cheaper to do it than to actually build and test the device. It's often safer to do that. Sometimes devices are things like um, spaceships and rockets and airplanes that if we don't know exactly how they're going to behave, they may crash and cause physical harm. They're also very expensive. They can be very complex and hard to build and hard to understand. So simulations give us this opportunity to look at them in a much more controlled environment. And we also need to look at computer simulations because most interesting things we look at are nonlinear, and the tools for analytic solutions, as we saw in an earlier module, really deal with linear systems. We'll wrap this up by talking a little bit about the relationship between computer simulations and state space models, and we'll talk about what components all simulations have to have. So what is a simulation? In essence, when we're talking about this in the context of dynamic systems and when we're talking about engineering, we're talking about a numerical solution to a set of differential equations. And in the context of this class, we're going to constrain ourselves to ordinary differential equations where there's only one independent variable, and generally that's time. There are lots of numerical methods out there to solve these differential equations. They date as far back as Euler. The most common one is Runge and Kutta. They came up with a fourth and fifth order system that works really well, and it's kind of still the bread and butter for most simulations. And then there's a series of algorithms that came out later that deal with more exotic systems. So why do we simulate? So that's a really good question, and we already discussed how to solve differential equations, right? We spent a lot of time finding it's called the initial value problem. If we know the initial values and we know the forcing function, we can predict what the response looks like. And that's an incredibly powerful method, and we spent some time looking at second order systems. So for example, in a previous chapter we looked at a spring mass damper system, and we saw how changing the mass, the spring constant, the damping factor, changes the response, changes the nature of the response. We can make these important connections between parameter values, physical values, and how the system will behave. So that's really very powerful, but it's very limited because it only works for low order systems, right? You get up into the third order and higher, it's harder to make those generalizations. We don't have those kind of parameterizations available to us, and it's also harder to actually do the math on it. It can be pretty tedious. It can also be tedious to do it with anything other than the most basic inputs, impulse inputs, step inputs, sinusoidal inputs. Those are pretty easy, but the world is full of all sorts of other inputs. So if we need to see the response to an arbitrary set of inputs, analytical methods can be difficult as well. There is this wonderful tool called the convolution integral, but for anything but the most simple ones, it often is solved numerically anyway. So again, the computer simulation approach suggests a good approach. But really, probably the single most important reason to do simulations is because the world is a very nonlinear place. Most of the tools we'll talk about in this course and in control systems course really deal with linear systems. So everything from Laplace theory to frequency response and a lot of stability theory really assumes linear systems. We've talked about how we linearize systems so we can use these tools. But when it really comes down to it, we need to check and see if these nonlinearities impact the way we apply the linear tools. So this is a really good check for that. Our simulations will almost always have the nonlinearities involved in it. There's no reason to linearize your model if you're going to do a computer simulation. And then we talked about this at the very beginning, right? We also simulate because experimenting is expensive. Experimenting can be dangerous. So if you do a really good job with simulation, you can learn a great deal about the system. But keep in mind that simulations aren't free. And it's pretty easy to kind of go down the rabbit hole and spend tens or hundreds of hours of engineering time to get a simulation, when for a simple system that maybe it does make sense to run a test or two. So there's always a trade-off and something to keep in mind. So here's one of the key points I wanted to make here, and that is that if we had to write a computer program from scratch every time we want to do a simulation, that'd be pretty hard to do, right? It would not make the program very cheap, and it would really decrease the value of computer simulations. And the good news is that there's these wonderful general programs that can be used for any arbitrary system. And I think it's worth asking the question, how could that be? How can a single computer program platform model just about anything we'd want to model? And the answer to that really goes back to state space models. We talked about this in a previous chapter. And that is that any system, any lumped parameter system can be expressed as a series of first order differential equations where the derivative of the variable is alone on the left hand side, and on the right hand side is a function of all the other variables of the system. These are of course the state variables of the inputs, and possibly time could be explicitly show up in those functions. It often doesn't. In fact, it rarely does, but we can do that. So expanding out that vector representation, we have a series of first order differential equations. And I think even by looking at this, you can start getting an intuition of what a numerical method might look like. So say for example, we know the values of these n state variables, these x's at some time 0, the initial conditions. And that means we know the inputs. That means we can evaluate that function on the right-hand side, all those functions on the right-hand side, for time t equal to 0, because we'll have a value to put in for x, and we have a value to put in for u. And if we assume those functions are constant for some small period of time, we can multiply those functions times that small period of time and get the area under the curve, right? Get the integral of x sub 1, and now we have an approximation for what x1 looks like at that next period of time, and what x2 looks like for that next period of time, and so on. And so that would be called like a 0th order approximation. That is what Euler's rule is. The rules that the algorithms we generally use make a higher order approximation for what those functions look like over time. But they're all the same thing. We're looking a little bit forward in time to and find the area under the curve of those functions to perform those integrations. So basically, if now all we have to do is write a program that takes this series of n functions and applies the same algorithm to them, regardless of how many they are, regardless of what the function is. We just have to specify those functions, and the computer program does the rest. So that's why we have these general purpose computer programs, and Simulink is what MATLAB uses. There are other ones available. There's systems that work under a program called Scilab, which is an open source package that comes from Europe, and there's several others, so I won't go into that. But they all have to have these common elements, right? And the first one is the obvious one. You have to have the model, some representation of the model. Sometimes it's just a piece of computer code that defines those functions. Often it's a block diagram, which is how Simulink represents the systems. There's an integrator or some indication of integration for each state variable. So if it's a third order system, there's 3 state variables. There'll be 3 integrators in it. There's model parameters. I'm using that term to refer to things that don't change during the simulation time. Things like mass, resistance, spring stiffness, and so on. There's initial conditions. Just like solving differential equations analytically, we need to know the values at some instant in time, and we'll call that time t equal to 0. That's arbitrary, by the way. You can call it any time you want, but the initial conditions are where we start our simulation. Most systems are driven by some external input. They don't all have to be. They can be driven we could just be finding the response to initial conditions, but often there's some input, so we have to find a way to define those in our simulation. Outputs, like state space theory, outputs are those things we're looking at. They're often the states themselves. They could be some combination of the states. And just kind of as an interesting philosophical statement, you don't really have to have outputs, but why are you bothering, right? The outputs are the things you're looking at. If you don't have outputs, you're wasting your time. So, and finally, this broad group I'm calling solution control parameters. Those are the parameters that govern the way the computer package solves the differential equations. Things like what algorithm are you using, what's the step size, what's your error tolerance, and so on. So that's kind of the beginning of our discussion. That's our summary that talks about the important parts of what control systems or what computer simulations are about. We're talking about solving a set of first order differential equations, essentially the state space model. And integration is the central part of the process. We begin and end computer simulations talking about integration. And they all have all these simulation packages have the same structure and feel. So if you haven't already, make sure you have MATLAB and Simulink running on your computer, because the next part is going to be walking you through the process of developing a simulation from the ground up. And I think it'd be very helpful if you had this video and your computer program running at the same time. So thanks.